All right, so we're moving on into part 3. But before that, how are we with homework submission? How many did not submit yet? Hopefully 0. Seriously, when are you going to submit? Is it because you have doubts and you need to ask questions, or really? Okay.
We hope that today's class will inspire us.
But no, so the homework for week 2, it really depends on only on what was taught in week 2, right? And the same with homework for week 3. So the assignment 2 is out. All right. I have also made available a recording because I won't have time to go through that material, which I made optional. And you should you choose to watch it, you should go through it after we finish this chapter in its entirety. And probably that won't happen today. It will happen next time. But let's see how much we can go through. And yeah, so in that case, do you need an extension? Do you think that the assignment was too difficult?
No, it was good.
It was good? All right. So those of you who haven't submitted, if you have questions at the end of the class, we can chat. All right, so today's chapter or class is about aggregation. We started talking about aggregation, and we discovered a very important thing last time, that inside a lambda, inside an entity, doesn't necessarily need to be a lambda, but it happened to be a lambda last time. So inside an entity, we can hide more stuff, other entities, which happen to be numbers in that case. But again, that was just by chance. And we kind of figure out from that example that it's important to do that systematically, right? To be able to do that systematically. And that was kind of an arcane way of doing it, right? It was kind of subtle, and we had to think about it, how it works, right? So we want more straightforward ways of aggregating data, right? What do we mean by that? It means that we create this entity that has other entities inside, right? And we're going to find, and this entity that contains other entities, they're essentially a container of sorts, right? And we're going to see that there are several types of containers, and all of them have different properties. And there's, if you try to compare them, right, there's different ones because we can use them for different purposes, and each of them does something better than the others. All right, so the need for aggregation is, we've argued in favor of that. If you think of just a person, how would you encode a person? It has a lot of attributes. It has name, first name, last name, maybe a suffix. It would have a date of birth, an address, gender, and so on, right? So all these attributes are what create the identity of a person. In Singapore, they would have a NRIC. In the States, they would have a social security number. They would be identified by some sort of unique string, and so on. And whenever we code with persons, we want that person to be an entity, right? I don't want to always see the multitude of features that the person has, right? Sometimes I want to see some of them, not all. And sometimes I just want to treat the entity as a single object, as something that is opaque. I can't see inside it, right? It just simplifies things. Okay, so we're going to learn several ways of aggregating data. And through the first 4, we're going to go through today, and the last one, objects, we're going to leave for later, right? So we're going to see sequences, collections where the order is important. We're going to call that sequences. They're also known as lists or arrays, but in Python, especially in Python 3, they're typically called sequences. And they're going to have some properties. For instance, we can change the objects inside that list. we're going to see a different one, which is called tuples, which are also sequences. They're also, the sequence is important, the order is important, but you can't change the objects inside. There are sets where the object is not, where the order is not important, and each object can appear only once. And then we're going to have maps. A map is very similar to a function in the sense that you provide a key, and for that key the map returns a value, right? So pretty much with a function, you put in an argument and you get a value back, right? And it creates this one-to-one correspondence between the key and the value. So we're going to go through all of them. All these 5 ways of aggregating data are standard in Python. They have special syntax, right? So the Python is trying to help us manipulate this kind of collections better by providing special syntax, and it's something that you need to learn to use very well. All right, so we're going to start with lists or sequences or arrays. A list or sequence or array can be specified as a comma-separated list of objects enclosed in square brackets. All right, so this is a list, and it is an object. We can name it somehow, right? We can give it a name. And then if we print it, we're going to get something like this, right? We can also evaluate it, and we're going to get the same thing. And it's about the same, that duality between printing and evaluation. In this case, the output is the same. It's not always the same, right? Printing and evaluating, but it so happens to be the same here. And now, what we need always with a container is to be able to access the elements inside. So, since this is a ordered list, and each element can be identified by its rank or index, right? We can provide that index to access the respective element. So if we add to the list the index and square brackets, we just get the element back, right? Notice that the index starts at zero, so indices start from 0 and go up to the length of the list minus 1, right? So this list has 5 elements, and we go from 0 to 4, right? If I would try to retrieve the 5th element, I would get an error. One very important feature is we can get sub-ranges or sub-lists. So this is a sublist, right? It's between the first and the third element, right? But it is inclusive with respect to the first element, to the first index with 1, and it is exclusive with respect to the last one. So the third element is actually not included. So this evaluates to 2 and 3, right? 2 and 3 from here. Okay, maybe saying 1, 2, 3, 4, 5 is not that. Might raise some confusion. So let's say 10 up to 50, and then when we perform the selection here, we get 20 and 30. Is this clear? So it's inclusive with respect to the first index, to the 1 here, and exclusive with respect to the last index. So you're going to see that this is what we really want. You're going to find it confusing in the beginning, but this is what we really want. In coding, you will see that it's a lot more comfortable, it's a lot more convenient to have things this way. Okay? Now, we don't need to specify both limits, right? There are implicit limits. If I leave the second limit, the last limit, unspecified, then the index goes up to the end of the list. So this one column will return, right, all the elements from the first. And when I say the first, I'm also thinking that there's a 0th element, right? So we're going to think that this is the 0th element, this is the first, this is the second, all right? So this will start from the first and go until the end of the list. We can also do the opposite, not specify the first index, right? in which case it will go from the beginning. Okay? One very cool feature is that we can specify indices counting from the end of the list. This is what differentiates Python significantly. It simplifies things a lot. So whenever I say -1 here, I'm going to count one element from the back. All right, and again, this is going to be exclusive. All right. So we're going to return 2, 3, 4. Why? So -1 is going to be this guy. This is -1, this is -2, this is -3, this is -4, this is -5. Right? So whenever I'm going to say -1 here, remember, this guy is exclusive. So this is -1, and this one is the one that we don't add. Right? So we're going to have 20, 30, 40. Okay? And we can use negative, so end-indexed elements in both positions, right? I can start from -2 to till the end. So this will return the last 2 elements of the array. So if I want to say, give me the last 2 elements of the array, this is how we do it. Okay? So this is about accessing contents from the container. We're going to see this with all the collections that we have. Now, we can perform elements between multiple lists. So since we have these containers, we can find ways of combining them together. The plus sign concatenates 2 sequences, right? So this is, right, 10, 20, 30, 40, 50, and I can add to it A and B. And notice the fact that the list doesn't need to be homogeneous. It can be heterogeneous, can have elements of any types together. This is also a feature that is unique to Python. Most languages will not allow collections or containers containing various types of elements. Okay? Now, it is not the case that the value of my first list has changed. My first list still has the same old value. Right? This expression, however, is a completely new list. I could actually call it my second list and assign it to that. Okay? So it's a completely new list. The old my first list is still the same. Okay? One thing that I forgot to mention, and probably this should have been mentioned above. This would have been better here, since we're talking about ranges. We can provide a step in our enumeration, right? Whenever I get a subrange, I can provide a step. So within this range, I will take every second element. Is clear? So if you look here, we're going from here up to here, but taking every second element, not every element. Right? We're taking B, then we take D, then we take F, then we take H. Why don't I go until I? Probably I should go until I. That's very true. I should go until I. So I should go until I, but then select every second element. Okay? So it's still up to H. I is not selected because it's immediately after H, right? No, you start at the first always. You start 1 and then skip, next one, skip, next one, skip, next one. So you're getting every well, when you say you get every second element, maybe my English is not good, but when you say I get every second element, right? So I get every second that I pick you, skip you, pick you, skip you, pick you, skip you, right? Okay. If I say every third, pick one, skip, skip, pick one, skip, skip, and so on, right? Are we cool so far? Okay. Multiplication. We've seen it in strings. It works with lists too, right? So we can create a longer list that are with instances of the same list concatenated together. All right. And when you look at a list as a concept, right? There are a bunch of operations. So we've already seen indexing, concatenation, multiplication, right? What else is reasonable to have about the list, right? So at least the length, at least to be able to get the size of the list, that should be an important thing, right? I couldn't write my own length, right? And the system should provide it for me. Okay? Not unless I knew a bit more about the internal representation, right? But Python will keep the internal representation of a list opaque, right? So then it has to give me some primitive to get the size. Always the size is a very important thing. There are a few goodies that wouldn't be necessary, but they're very convenient. There's min and max, right? And this min and max only work for homogeneous lists, however, right? Because I don't know how to compare A and the number 1. So if I were to try to apply it to, where's the list that was heterogeneous? If we were to apply it to this list, it will not know how to compare A and. But if we have a list of only numbers, or if I have a list of only strings, then they can be compared, right? The numbers can be compared using arithmetic comparison, and the strings can be compared using lexicographic ordering, which is one string is smaller than the other if it would appear before it in the dictionary, right? So it's a dictionary order. So if string A appears before string B in the dictionary, then string A is less than string B. So we have these goodies. If they didn't exist, we could very easily write our own, no problem. Now, important paradigm shift. We can change the values. Okay, so we have already changed the list to 20, 30, 40. So as to make it clearer that when we select the element and when we use the index, but otherwise the index and the element are always the same, right? So now this operation is going to put 100 here. So this actually changes the current list. Doesn't create a new list, right? From this point on, the current list has changed, right? So maybe this is something worth trying. So let me say that list L is, let's use A and 3 to make things, and 3 without a string. Okay, and now I can say L index 1 is assigned let's make it another B. All right, and now if we evaluate L from this point on has completely changed, right? Let's have L2 be 10, 20, 30, right? And then I can say again L2 index 1 is assigned A, right? So now L2 has A in the middle, right? Okay, so this is a very useful, it's a very useful property. Thing is that it's more dangerous than you might think. So, what? No, you can't do it. You can't undo it. But why would you want to undo it? So the trick is that I can always create a copy, right? L3 equals L2 dot copy. Is it like this? Yes, it's like this, right? So now L3 0, I can make it 40, right? So L3 has changed, but L2 is the same, right? So it's up to me to make a copy and keep it the same, right? But it's more dangerous because of other reasons, right? Because the world nowadays is concurrent. We have multi-core computers. We have things going in parallel, and whenever data structures can be changed from different streams of computation, that leads to non-determinism, right? So it's a bit advanced, but in general, we want to have the option of not changing things, and we're going to see with tuples that this is possible. Okay, but we're going to take advantage of this property a lot. Okay, other things we can do. We can count an element, right? So after we have changed this value to this position to 10, right? We have a list that has 2 instances of the number 10, right? And we can use the count to count how many occurrences of the argument do we have in the list. Now, this is a strange notation, all right? But we have seen a little bit of that last time, okay? So let's repeat that. I'm gonna define a list. We already have a list. Let's say L. Is L still there? Yes. So one thing we can do is help L, all right? And the help L is going to tell us quite a lot of things about a list. And this is actually any list. It tells us that this is from class list. And let's ignore for the time being these double underscore functions, all right? So they're a bit special. But we have a few functions here. We have a few entries that appear as if they were functions, and for some reason I can't select. This idle format is very bad. So we have append, we have clear, we have copy. We have already seen copy, right? We have count, and this is the one we're looking at, and we also have extend. Well, actually, we have several. We have index, insert, pop, remove, right? And we're going to talk about all of them. Now, as I was telling you last time, every object comes with all the operations, or with a set of operations that it can perform, right? The operations are inside the object. This is how we think about an object. And when we talk more about object-oriented programming, we're probably going to understand this issue better, because we're going to define our own operations that we put inside the object. But we have seen this with integers, right? If I say help apply to 3, I get also, a long documentation where we see a lot of functions. Now, the functions here, they're all special, right? And last time we have seen that if I do something like this, I can perform addition, right? So instead of 3 plus 4, right, this is the vanilla expression that Python allows us to type in, but in the background, it performs this operation, right? It takes advantage of the operation that sits inside the object, okay? All the objects have this kind of operations, and we can take advantage of them. So one is the count. So for instance, if I have a list, let's do a long one, right? 10, 20, 30, 20, 30, and 10, right? And now I can say count 10. So count is an operation that the list has. And I'm going to have that it has 2 occurrences of 10, right? And if I'm going to say 20, it has 3 occurrences of the number 20, right? We can always find out what's inside the object. I can always say help, or actually even faster is to say dir. So dir will give me just the functions without the documentation. So if I say dir of the empty list, because it's just a list as any other, right? We get all of them. So we're interested in these ones: append, clear, copy, count, extend, index, insert, pop, remove, reverse, and sort. All right. So let's try all of them. So I'm going to define again a list, and actually let's just reuse this one. So let's say this is L, and I'm going to say L dot append 100. Okay. What do you think happened to L? Right? So L got extended by 100. What if I do L dot append of 1 and 2? What do you think is going to happen? Louder. All right, so you're probably going to be surprised. You're not. It's what? Explain this. So append adds 1 element. Now that element can be a list. So we can have a list of lists. No problem with that, right? So 1, 2, comma, 3, and 4, right? So if I take this list and I take index 1, let's say, I'm going to get 3 and 4, right? Because the outer list has, and again, I cannot select, the outer list has 2 elements. This one is the first element, and this one is the second element, right? There is. You see here extend, right? So I can say extend. Okay? Again? You can say insert. So let me see exactly the index object. Okay, so if I want to insert, right? So I can say at index 0, I want 200. No, so that you can't, but you can always add the second list to the first, right? So you can always do this. Right? So if I have a list L, I can always say L is equal to L plus what should it be? 1,000 and 2,000. Right? So now if I look at L, now this is much less efficient than extend. Right? Can you figure out why? Yes. So essentially it makes a copy of this, copies this entire thing. Oh man. I don't know why I have to sort this out. So it copies this entire list and adds 2 elements, right? Yes. Again, again, it would not be the fastest way, right? So this would be the fastest way. It's actually faster to say add the first element and then add the second element, insert the first element and then insert the second element, then concatenate the list. Right? So whenever performance is important, but you're absolutely right. So you can play with this kind of expressions as much as you want, and it's as long as performance doesn't matter, they're perfectly fine. They're actually safer because you don't change lists, but actually you create new lists, which from a point of view of multi-threading is multi-core computing is safer. Are we okay so far? Cool. What else was there? No, let's finish these functions. They're important, right? So copy, count, extend, we've seen. Insert, we've seen, right? But let's see it in full-fledged form. So if I want to say, right, so I could insert at position 3, and let's insert a string this time, right? So notice how it works. This guy, ABC, becomes the third element. The third, by the beginning of the list, is the 0th element. That's always a bit weird. But this guy will have the index 3. So everything is shifted so that this guy becomes the element with the index given here. Okay? What else was there? Pop. All right? So what does this do? It removes the last element and it removes it. It returns it, right? So it gives it back to you, but at the same time, it has the side effect of removing it from the list. So this is now a rather complex function. It has two things. It does two things, right? It has a return value, which is this 2000. Okay? And it also removes on the side, as a side effect, it removes the element from the list. Can you understand this? Right, that we can perform the computation by returning the result, and we can also perform computation by mutating a piece of mutable data. Right, so two things happen. Remove a value from the list, that's one thing, then return that value as a result. We're going to see a lot of these, so you have to be prepared. Remove. Remove is the opposite of insert. So I can say, let's remove the ABC now. So I can say L.remove at position 3, right? Oh, no. This doesn't remove at a position. How do I remove from a position? It doesn't remove from a position, but I actually remove an element. Right? The first one. But we cannot remove from a position, really? None of the special ones don't do that. All right, index, we haven't seen index. So let's see the index of 30. L.index. Right, and we get 3. So it would search, and again, it will give us the first occurrence. Reverse. Reverse is simple. So you see them reversed. And then there's sorting. But sorting will only work if the list is homogeneous, right? So if I say L dot sort now, we're gonna see that this, which is one element, this 1, 2 list, this list made up of 1, 2, which is not a number, cannot be compared with numbers. So let's remove it. And then we can sort. Okay, cool. So these are sequences. Let me see if there's anything else. Oh, comparisons. All right. So well, let's just go through them. So comparison is done by lexicographic order. What do we? What does that mean? So let's say we have elements that have a predefined ordering. So if we have numbers, we know what the ordering between this guy and this guy is, right? And also if we have strings, we know what the ordering between this guy and this guy is, right? So now if we have a list of ordered elements, you can imagine those elements as being letters in some strange alphabet. And, right, the letters of the alphabet are ordered, right? So our new alphabet is ordered by the rules of the ordering that we have. And if the word represented by this sequence would appear in the dictionary, in a hypothetical dictionary, before this other word, then the comparison is less than. Otherwise, it's greater than, right? So it's very good that we can compare sequences, right? But they have to always be comparable elements. So 1, 2, 3 will come before 1, 2, 4. Why? Well, 1 is equal to 1, 2 is equal to 2, but 3 is less than 4. Right? So we go from left to right synchronously, position by position, and as soon as we find one where they are different, whatever comparison is there, that's the comparison for the entire list. Right? Shorter strings are or shorter lists are always less than longer lists, and so on. So if we have 1, 2, that will be less than 1, 2, 3. Right? So the opposite of that is false, obviously, and it works very well with numbers, and it works very well with heterogeneous lists, as well as the elements on the same rank are comparable, right? So this is a heterogeneous list as well as this one, right? But this guy is comparable with this guy because they're both strings, and this guy is comparable with this guy because they're both numbers, so the comparison works. Yep.
So does it check the length of the list first or the element?
No, it just scans. So no matter what, you're going to incur a running time that is proportional to the shortest list.
Can you do 1 4 greater than 1 2 3? What would that?
1 to 3 is smaller. Yeah, let's do that. No, so it's the dictionary rule, right? So 1, 4 is going to be greater than 1, 2, 3, right? Then you get an error. 1a less than 1, 2, right? So 1 and 1 compare fine, but a and 2 cannot be compared, so then you get the error. Okay?
How do you compare two lists with different amounts?
You just go from left to right synchronously in both. So if you go and you couldn't find elements that are different, as soon as you get the shortest, at the end of the shortest one wins. Right? Otherwise, you keep going and you find the first position when they're different, and the comparison on that position wins. Okay? Okay. Now, there's a new important construct, and then there's a new important concept attached to that programming construct. So all these collections or containers, as we would call them, they're typically called collections. They're collections of elements, right? It is important to be able to go through all the elements exactly once, right? Perform one operation for each element, right? And that kind of approach is called iterating through the collection, right? And then there is this general thing called an iterator. It's a general concept. It's a general class, and all the collections are actually instances of iterators, right? So even the set that doesn't have order, that doesn't have an order, we know from mathematics that sets don't have order. Python will put them in some random order and allow us to iterate through the set. Consider each element. So if, say I want to print every element once, right? So I can iterate from through the collection and print every element once, and I can do it even with a set. And what's going to happen with the set is that the order is going to be random, but still I can go and put my hand on each element once, exactly once, right? That is what is guaranteed. So this is called iteration, and whenever we want to iterate, Python allows us to do that via a for loop. So we can say for, we can invent a variable name which becomes the sample from the collection, and then we iterate through all the elements in this collection, right? So I, in turn, will take turns in becoming 1, then later 2, then later 3. And then for each instance of I, for each incarnation of I, whatever is inside the for loop will be executed. So this, for instance, will print each element inside the collection, right? So we could very easily do this with a while loop, but it will be a larger piece of code, okay? So let's say that we want to square all the numbers in a list. And actually, this code doesn't really care that this is a list. I'm saying a list of numbers here, but I might as well put a set or a tuple. So we start with an empty list, which is going to be the result eventually. You see, eventually we're going to return the result here. And then iterating through this list of numbers, right, we take k to be the sample, the iterating sample, right? And then what we do is put in the result the square of k, right? So if this list of numbers is the numbers 1, 2, 3, k will be first 1, then later 2, then later 3. And then what we're going to put in the list is 1, then 4, then 9, right? So we're going to end with a result that contains the numbers 1, 4, and 9. Yes? We're appending. We're appending. We're not appending to the head. We're appending to the end. Right? If you're coming from a camel, maybe we should have a discussion at the end of the class. All right? So I know where you're coming from, and I know that if you were in a camel, you would have to reverse it. We're not putting together a head and a tail. We're actually appending one element at the end. Okay? So let's see this one working. Okay. Right, so if I'm going to say square all right, we get the list of squares. Okay, clear? Well, let's try to write it with a while loop. And then you tell me whether it's easy or not. So I would say result is the empty list, and then I'm going to define an index, which initially is 0, right? And I'm going to say while I is less than len of list of numbers, right? I'm going to have result dot append of list I, and then I'm going to say return result. Okay? So that would be the while loop variant. Have we written more? Which one do you like better? Yes? And we need to increase I as well. Yes, very good. See? And that's a very typical mistake, which because I never use while loops, I tend to make very frequently. Okay, so now which one do you like most? So the 4 is better, right? Okay, let's do another one where we sum up the a list of numbers. So interesting question. What happens if the list is empty? What's going to be returned? The empty list, right? So the empty list as an argument doesn't seem to be a very important one, right? But it's a corner case, and we definitely don't want our program to bomb, right? So we should always be careful what's happening in that case. All right, and we're going to see that in this case it's a bit more interesting. So we're going to sum up the list of numbers. So let's start with a result, which this time is an integer, has the value 0, right? And again, we're going to iterate through the entire list of numbers, right? And for each sample k, we add that k to the result. So we're going to add the k's one by one and end up having, in result, having the sum of all these numbers, right? And then we can return the result. So let's try this one too. And I'm going to avoid typing the list again. And we get the result. In this case, what do we get for the empty list? What am I going to get here? 0, right? Is that reasonable? Well, depends on what you call reasonable, right? Well, why would you return any number at all, right? So it's a bit weird, right? So it's a bit weird. So for empty list, you're still giving back a number, right? So it depends really on what you call reasonable, right? So by definition, we can say the sum of all the elements in an empty list is 0, right? So you can say mathematically that that's the case. Actually, by convention, that is the case. But in this particular case, it's very much up to you to think whether that's reasonable or not, right? Because you have a. So, for instance, let's say I want the minimum of the empty list. What should that be? So minimum of the empty list is 0, but minimum of a list containing -1 is -1. Is that reasonable? Right? Yeah, no, so I mean, I'm just saying, the answer is not always very obvious. So what's standard in computer science is that a minimum of an empty list is an error. All right? So if I say min right? It's an error, whereas min of 1, 2, right, work correctly and gives you the smallest number, right? However, for sum, so there is a function for sum, right, which is predefined, we would get 0 and not an error. So by convention, this happens, but again, it's what you consider reasonable, right? It's up to you to define it. And it's always the case that you have to think about it, right? You can't leave these cases out floating. All right. So is this clear? The use of the for loop and the concept of iterators, because you're going to see later that instead of putting a list here, I'm going to put a tuple or a set or a map, a dictionary, as it is called in Python. So just let it be understood that whenever, and it's important for you if you design other kinds of collections, which you might, to provide iterators for them, right? To provide a way to enumerate all the members in some order. It doesn't happen if there's no standard order, just pick a random one, but to allow everything to allow an operation to be performed on every single element of that collection. All right, so we're going to learn quickly another type of iterator, which is a range. All right, and the range is a way of us to create sequences of numbers without having them in a list. So this is the syntax, right? If I want all the numbers between 1 and 10, right? It's this is what we get. So I can say R equals range. If you ever did anything or played with Python 2, you should know that there is a range in Python 2, but Python 3, the range in Python 3 is equivalent to the X range in Python 2. If you don't have to, if you've never played with Python 2, don't worry about what I just said. But if you are, be aware of this difference. What is R? That's what it evaluates to, right? It's just what the system prints. So it is not the case that all the numbers of 1 and 10 are inside, because all the numbers between 1 and 10 will take some memory, right? And obviously 10 numbers is not that much, but I could put 1,000,000 there or even 1,000,000,000. And I don't want to expand this collection immediately and have all that memory occupied, right? So this guy will lazily give me one number at a time whenever I need it. All right, so it is a sort of an optimized sequence. All right, so let's do the same. So because a range is an iterable, we can use it inside a for loop, right? We can say for I in R, print I, and we're going to get all the numbers. Notice that this guy is exclusive. So that's always the rule. First one is inclusive, so the beginning is inclusive, the end is exclusive. Okay? We can add a step. Okay? And actually, one interesting thing is, oh, or not. I think there was a way of creating an infinite range, but maybe that's an advanced feature. I can do only one argument, in which case the first what is missing here is the beginning, right? So I have not specified the beginning. I have specified the end, and the default beginning is 0. Okay, which makes sense because a lot of the time this is what we want. Yes, but in which case you might get infinite, right? So if I say right, and now if I'm going to say for I in -1, and it will just go into, oh, it doesn't go into infinite loop, which is good. So it's empty, it's an empty range. No, as you can see, no. Yeah, I kind of expected the same. All right. Now, one thing that we have to, we learn and we'll see for all the collections is that we can commute, we can convert between them very easily. So I can very easily say list of R, and I'm going to get a list, right? And later you can say tuple of R, and you're going to get a tuple. We're going to see in a minute what, and I can see set of R, right? And I can convert between these as I please, right? These conversions are actually not instantaneous. They take time. They typically take time that is proportional to the size. The larger the collection, the longer the time. Okay, clear? Yes? Tuple you can't change. Set, you cannot change inside anything, right? So that's a useful thing. Set, no. You can create a new tuple with the addition, right? So I can do. We're gonna see in a minute. Let's not jump to that. Set contains each element once, right? So if I create a set with multiple occurrences of one element, only one instance, one, and I'm going to get. Okay, so it contains unique elements, and sometimes if I want to make the elements unique, I only want to keep one of them. That's a very useful thing. Yes, you just saw that, right? So any iterable, so when I say list, this can be any iterable, including a tuple. Right? When I say tuple, this can be also any iterable, including a list. Yes. All right. But again, so this is not a. So this requires time proportional to 3, right? If you have 1 billion elements, time proportional to there will be 1 billion operations inside. Right? It doesn't come for free. So you might be thinking that, oh, if we can so easily convert between all of them, why not just have one, right? So they actually all serve different purposes, and conversion between them is not for free. So you might just want to keep the one you have as it is. All right. So let's learn one higher order function, right? Because there's now a recording about higher order functions, but we're not gonna. It's optional. We're not going to go through it in class. So let's try just one thing, right? So I want to apply generically some function f to every element in the list and collect the results. So for instance, I want to cube all the elements in a list. Right, so I have 10, 7, 12, 2, and I would like to produce the list of 1,343, which is 7 cubed, 1728, which is 12 cubed, and 8, right? So you see, I want to come up with a procedure so that it's generic. I can provide here any function, and that function gets applied to every element in my list, or iterable, right? So how do we do that? Let's write that function. We call this function map. So this is an operation called mapping. I'm going to take a function that I want to apply to every element. This is my iterator. I start with a result which is initially empty, and then I iterate through all the elements in my iterator. And what am I going to put inside? I'm going to put inside f applied to k. Right? So this is a generic f. I can have any function there. I apply it to k, put the result in my result list, and then return the result. Right? So this is a very typical type of processing. And from this point on, instead of writing this entire loop, I can just write this expression. Okay? Well, it's actually defined. It exists. We do have a map. So map of x times x, list of 1, 2, 3, 4. And what this guy gives me is an iterator. So if I want to see the content, I have to convert it into a list or tuple. Okay? But, you know, I don't, so only if I want to see it, right? I mean, another thing I can do is, for instance, right, the result of map is an iterator, print I. Okay? So this guy here is an iterator. I have to convert it into a list or tuple only if I want to see if it's inside, what's inside. Right? This is an iterator. Yeah, that would have been a bad name, but that would not have been the... Yeah, no. So map is a predefined Python function, right? It exists in Python without you having to define it.
Oh, really?
Yes. Nevertheless, we are seeing it here. So let's call this my map to be more explicit, right? So we're defining a function called my map, but the map exists already in Python.
So
Right?
if I didn't define my map and just copy the my map lambda on the idle, it wouldn't.
No, it would. So if you're saying, oh, if you just copy pasted this, right? Yes, this will not work. Sorry. Right? So my map doesn't exist. Okay, let's try another one. So this function is the function that adds two numbers, right? And if you think that this is ugly, you can also try to use int.add. We discussed last time that this is available, and it's a function that adds two numbers. That's how Python actually adds numbers, right? So I would like to sum up all the numbers together. All right? All these numbers together. So I want a function, this fold, I would like it to perform the following operation. Now I'm just going to use plus because it's easier, right? The operation that I want it to go on here, we have 0 here, right? So remember, we want 0 plus 10 plus 8 plus 12 plus 1. We want to perform this operation. But now think of the fact that the list may have any numbers of any length, any size of the numbers, and this element here might be anything, right? But I want to produce this expression. And then this operator, maybe it's addition, maybe it's multiplication. How about if I say mul, immediately what we perform here is star, right? So we get the product of all these numbers. And you're going to say, oh, but it's 0. So then I'm going to go here and replace this by 1, replace this by 1, right? So you kind of notice, kind of understand the versatility of this function. It allows you to put a binary operator between the elements of a list, right? So we're going to say, why did I put brackets? Well, because I want to show you the order of the operation. In the case of star as well as plus, the brackets don't count because this is a commutative and associative operation, right? So what we really want to do is to put the binary operator between all the elements of a list. Now guess what? The list might be empty. So I have to have a result for when the list is empty, because we don't know, there's no predefined result for that, right? Well, we are doing it, right? So at this point, so let's use the function first, and then let's worry about how we define it, right? So it is defined there. So if I say fold int 1 110, what do we get? Yes, this would be 10 factorial, right? If I say int dot add, and I say 0 here, right? And I put any list here. What I get is the sum of the elements of the list, right? So I have factorial, I have the sum, yes?
So you can't write fold in this add. Like add on its own is not defined.
Actually it is. Let me, if I remember the package. Yeah, so it is. So if I import okay, so if I say from operator, right? So this is, now you have a nicer name for add.
And it doesn't matter
Well, it's still plus inside. No, so it does, because there's a very specific order of operations, right? So for you to understand what's going on, it's easier if I write it in this form, right? But each of the stars happens in a specific order, right? So we first perform this one, and then this one is performed, and so on and so forth, right? I could have a fold where the operations would be performed in reverse order. I could start here. This would be the first, and then the next one would be here. I could equally well do something like that, right? So by virtue of the fact that I can only take 2 arguments at a time, right? At all times, I have to pick which 2 arguments I should apply it to, right? So it so happens that if I pick an argument, an operator that is commutative and associative, right? That order doesn't matter, but the computation proceeds in a certain order. There's no way to avoid that order, right? And then since I can put anything here, right? For some operators, that order might be important. For instance, if I use a minus, it matters whether it's from left to right or from right to left, right? Yeah. No. The short answer is no. Typically in Python you would not use recursion for that, right? For a very simple reason that there's no tail recursion optimization. You probably know what that is if you're asking this question, right? So Python doesn't have that, so nothing will be implemented recursively. Everything will be a for or a while loop inside, right? So what I would normally do to make it run faster, because here we're using No, so here there's, I mean, there's no recursion, right? For fold. For map, we have the problem of creating a list, but fold has no recursion, and there's no need to worry about recursion in Python. Okay. So recursion is useful as a problem-solving method because certain solutions are simpler when you think of them recursively. But unlike OCaml, recursion is not a main tool of performing iteration. Okay. Well, so I have to. What do you mean it doesn't do anything? So what if? So let's use add here, and one, and what if I have an empty list? What should I be returning for the empty list? I need a result for the empty list, right? Would you prefer that there will be an error? It's again a matter of convention, right? So the question is, what should we be returning for the empty list? Give me the value that would be reasonable for the empty list. The function itself cannot know what that value should be, right? It's up to the user to decide what it is. Okay, so the one that you're not thinking, you might not be as immediate. So let's do minimum. Lambda x y x if x less than y else y, right? And then I'm going to start from minus a very small number, all right? And then let's take a list of 2, 4, 3, 5, 7, 6, 1, 9, and that should have been commas. And what are we going to get here? Hmm? Yeah. Oh, sorry. Mistake. It's going to be a very large number. Okay. So what are we getting here? We're getting the minimum of the list, right? So you see, with this fold, we can actually compute the minimum as well, right? So there are many computations that we can do with this fold. Yeah. Where do you think that? So what I'm going to do here, let's call this is the minimum operator, right? So let's denote by hash the minimum of the number. 1 hash 2 is the minimum of, actually hash is not good because it's $1 2 is the minimum of between 1 and 2, right? So what we're doing here is this very large number, $2, $4, $6, $78, $3, right?
What I'm asking is that how is this breaking down the elements of the list when you're not in a function like, I don't know, like, what do you say, in a function that takes out the first element of the list. Cost, right? Yeah. You're not putting it a cost or anything. And then, or like, so shouldn't you like put either like brackets?
So what do you think these x and y will be?
So x and y are dependent on the inputs that you give, right?
All right, so let me take this function. Okay. And now I can apply it. So what would you like to apply it to? What do you think it's reasonable to apply it to?
I think you should apply it to, yeah, something like that. For if you're comparing them both together.
Right? So why would you want pop? This is a function that,
Yeah, because in this case, both of them are in. So
right?
you can compare between an int and an int. But over there,
Right? So I'm going to compare between, first time I'm going to compare between this int and this int.
no, but how does it know to mix back that int from the list? Why does it not compare one to relevant with this list that has 2, 4, 6, 7?
Well, have you looked at the definition? This one.
Oh, it's good.
Right? So I'm going to start with a result that is this initial value. And then I'm going to replace this result with f applied to result nk.
And the thing over there is a list.
List, iterator, yeah.
Okay, but in so
Yeah.
So in the second example that you oh, that's not fold. What I'm actually asking is if you put fold and then all of this and you compare two integers, then it's not work, right?
If I put fold,
So if you write everything the same as it is, but instead of the list, you put and instead of the list, you just get a number, like 2.
yeah, it will not work, of course,
Because then
because it's not an iterator. So this now has to be an iterator, right? Because my assumption is that this is an iterator because it appears in a for, right? List, tuple, set, range, anything that contains more stuff.
do you think you can make it more generic? So no matter what you get,
Yeah, you can, but fold has a standard meaning, right? So whatever it is, you should give it the name that reflects what you're doing with it. You understand? So you definitely have the freedom of doing it. What we're trying to do here is implement a standard fold function, and I'm trying to teach you that this is a valid computation pattern. But if you want to define a different one, yeah, by all means. But then you should name it something that reflects. Yeah. Okay. All right. So we've kind of seen this, right? So we can define factorial. We can define minimum. All right. Let's see if we have enough time. Let's try to get through the sieve of Eratosthenes. So let's try to print the create an iterator with all the primes between 0 and n. Okay, let's see if we can do that. How does the sieve of Eratosthenes work? Right, we start with all the numbers, and then with all the numbers from 2. Right, 1 is not a prime, and we have to. And then we look at the first element in the list, which is 2, and then we start removing from the list, not removing, actually stamping or barring from the list all the multiples of 2, every second element, right? We don't want to remove it because we don't want to make the list shorter. We want to keep the indices, right? We're done with 2. We move on to the next guy, which is going to be 3. And then we stamp on top of every number that is a multiple of 3. We go every 3 places. Some numbers have already been stamped. So 6 already has already been stamped, right? If we put the stamp again on an already stamped number, it doesn't matter. It's still stamped. It's still canceled out, right? Then I move on to the next one. Remember, 4 is already stamped because it's a multiple of 2. So we go to 5. And then I remove all the multiples of 5, right? So this is how it works. So we're going to start with a list of candidates, right? Which we make a list out of a range. And we go in decreasing order. All right? So we go in decreasing order. We're going to have a result. All right? And while this list is still non-empty, we pick one element from the candidates. Right? So you put them in reverse order, right? And and this is exclusive. So 1 is not there. Right? So we go from n to 2. Is that clear? So the first number we extract is 2. So I take the number 2, right? And then what we try to do is we remove the multiples. Okay? How do we do that? Well, the multiple of I is I times something. What is that something? What does that something need to be? Something between 1 and some large number, right? So this needs to be conservatively large. I have to find here a value that is large enough, right? Yeah. But then you're going to perform idle operations, right? So you want to go up to n, fine. You can go up to n. Just that it's going to take longer, right? So as long as this number appears in the list, we remove it. Why do we have to check whether it appears? Because we cannot remove something that doesn't exist. It yields an error, right? So we keep doing that until we have gone through all the numbers, at which point the result has all the primes. Is this clear? So this is an example computation where you can use a list, all right? And notice one thing that so you can evaluate it yourselves. The result is going to be here, right? This is an example, and we're going to start doing this more and more, where we don't print stuff. So far we didn't know how to aggregate stuff. So in the homework you were asked to print stuff, right? And in assignment 2 even more so, you're going to be asked to print stuff. But now we want to return stuff, right? Because we can aggregate numbers. Previously, the only thing you could get your hands on was one number. So then if you say, for instance, you compute primes, all you can do is you have one prime at some point, so you have to print it, and then you print all of them, right? Now we can aggregate all the results in one big collection and return that, right? So that becomes a better way of returning results. All right. So again, I start from all the lists written in reverse order. When I pop from the end. So I start with 2. I'm going to pop 2, then pop 3. I'm going to not pop 4 because pop 4 has been removed. I'm going to pop 5, right? So I pop 2, and then inside this loop, I remove all the multiples of 2, right? I go from 1 to some large number, and undesired is a multiple of 2 currently, right? So this is current times that sequence of numbers. Those are going to be multiples of 2. Remove all of them. Clear? If they exist in the list, then we remove them. And actually here I should say undesired. This would be better. Right? Then we move on to 3. If it and remove all the multiples of 3, right? Then 4 is not going to be here anymore. We're going to move on to 5, right? And notice that because of the order in which we append the results, they are going to appear in increasing order. I start with them in decreasing order, but I pop from the back. Why did I start with them in decreasing order? Because I have a pop that removes from the end. I don't have a similar function that removes from the beginning, which is what you were asking, right? At some point, whether there's a function that removes from the beginning. All right. Also, this is a good example of a function of a computation that has nested loops. All right, we have a while, and then we have a for inside the while. Right?
Also, the range parentheses n 1 minus 1
But this goes from n to 2.
and 2.
2.
How do you know what where 2 is?
Because this is 1, right? It's exclusive. Ranges are exclusive. 1 is not there. Right? So if I say range 10, 1, this will go and minus 1 as a step. This is minus 1 is a step, right? I'm going to go and let's say 3. I don't want to type that much. So I'm going to go to 3 and 2. 1 is not there. 1 is exclusive, right?
Yeah. And how does I don't know what n is?
Well, this is n,
Yeah.
and whenever I call the function, whenever I invoke it, n becomes 100, right? Cool. Again, it evaluates to these numbers, right? Okay, let's okay. So it returns a list with all the primes. Does everybody know what primes are? I'm like, all right. Oh, well, they're more difficult than non-nested loops, so they require a bit more mastery, right? So you have to practice thinking in terms of that. All right, so we're going to continue with this next time. Homework.